Now let's look at what are called quadratic forms. All right. So there is a notion of what are called Hermitian forms also, but they are similar in nature. All right. So what we are saying here is that I want to understand, given a matrix A which is n cross n, I want to look at x star Ax. Is that okay? A belongs to Mn of C, and I want to look at what is x star Ax. Is that okay? The idea appears at many places. Geometrically, if you want to see, we want to look at, so geometrically, if I want to understand geometrically, what we are saying is that I am looking at all x belonging to Cn, so that Ax star Ax is equal to 1. So I want to plot the curve, what this curve is or what this object is. I want to understand that. Fine. And we have been doing it in our school, that we had this x belonging to R2, so that x transpose Ax. So for certain choices I could have A in certain ways. For example, x square by A square plus y square by B square is 1. I could also have x square by A square minus y square by B square is 1. Fine. X square plus y square is equal to 1. We had such things. All right. Fine. So you see that you have an ellipse, you have a hyperbola, you have a circle. All right. We will see that when we want to generalize these ideas, in place of looking at A here and x here, we can have something more also. So that will come afterwards. So we can also look at what I am trying to say is x transpose x plus x transpose some B is equal to a constant 1 or something, because look at this, this is a 1 cross 1 matrix, this is also 1 cross 1. So I can write it as 1 or some C here, and then try to look at the graph, look at the curve that this represents. And once I have this, then the notion of parabola will also come, the notion of pair of straight lines will also come in 2 dimension. Similarly, in higher dimension, what it looks like, and it has got a lot of applications to understand this part. All right. So let's start with our definition. So definition. So I'm going to take A belonging to Mn of C. All our examples will be over real numbers. Once in a while I look at complex numbers, but the definition is over complex numbers. All right. Fine. So let's also definitions. So matrix 1, A is said to be positive definite. Recall I had used this idea of positive definiteness at the time of inner product also. So A is said to be positive definite if x star Ax is greater than or equal to 0 for all x belonging to Cn, and x star Ax is 0 if and only if it implies that x is the 0 vector. Is that okay? This is what positive definite means. Note here that when I say that x star Ax is greater than or equal to 0, what we are saying here is that x star Ax belongs to real number. All right, because I cannot make any comparison over complex numbers. So I am already saying here that x star Ax is a real number and x is in Cn, and that implies, so this will imply, this condition will imply that A star is A, that is A is Hermitian. All right. So when I am looking at Cn over C, so when I am looking at Cn, I just need to say that this is greater than or equal to 0. All right. I don't have to put any condition, because that condition itself implies that A is Hermitian. So this condition implies A is Hermitian. Fine. But when I want to study only over real numbers, only over Rn, all right. So if I am looking at x transpose Ax greater than or equal to 0, then whatever A you choose, this will always be a real number. All right, whatever A you choose. So when I want to study quadratic forms over real numbers, I will assume that A is equal to A transpose. So A is symmetric. All right. So I may not use the word symmetric again and again, I may not use the word that A is Hermitian again and again, but in this chapter for us it is going to be symmetric. A is symmetric or A is Hermitian. Fine. I am not going to check this part. I would like you to do it yourself, that if x star Ax is greater than equal to 0, then A has to be Hermitian. Try that out yourself. Fine. Let us go to the next definition 2. So here I looked at what is called positive definite. Now there is notion of positive semi definite. A is said to be positive semi definite if x star Ax is greater than equal to 0 for all x belonging to Cn. All right. In short, we write it as PSD. This in short is written as PD. Fine. Third definition. Let me write all the definitions here. A is said to be non-negative definite. Or did I write non? I have said no. I have said negative definite, negative semi-definite. So I have not used the word. I have used negative definite. Negative definite ND if x star Ax is less than 0 for all x belonging to Cn. So just the reciprocal of this part, or not reciprocal, the negative of this part. Fourth is said to be negative semi definite. So NSD if x star Ax is less than equal to 0 for all x belonging to Cn. And the last one, fifth, A is said to be semi definite or indefinite, x is said to be, I think I have written indefinite if it is neither of these. All right. So if there exists x and y belonging to Cn such that x star Ax is less than 0. So there are some portions where it is negative and there are some places where it is positive. All right. So both the things happen, negative as well as positive. Is that okay? So indefinite means we are not sure whether it is on the positive side or we are in the negative side. So positive definite means that everything is on the right hand side beyond 0 in some sense. Semi definite means 0 and something. Negative definite means you are on the left in the real line and so on. Is that okay? So let us look at examples. One. So I define A as 2, 1, 1, 2. So it is a symmetric matrix. Fine. I would like you to check that x transpose Ax is greater than or equal to 0 for all x not equal to 0. I would like you to check that. Try that out yourself. I take complex example 3, 1 plus I, 1 minus I and 4. So now look at x star Ax. So this will be greater than 0 for all x not equal to 0 and x in Cn. Here I can take x in Cn, but I can take in Rn also. Whatever you want to see, you can do it. Fine. And how do I check this part? So let me check this part for you. Fine. So let us look at the eigenvalues of this matrix. So let me look at eigenvalues of A. So I want to look at determinant of A. Determinant of A is 12 minus 1 plus I into 1 minus I, which is 12 minus 1 minus I square, which is 12 minus I think 2, which is 10. Fine. And trace of A is 3 plus 4, which is 7. So the eigenvalues of A are, so the eigenvalues satisfy lambda 1 plus lambda 2 is 7 and lambda 1 into lambda 2 is 10. So, I can see that the solution for this is going to be 5 and 2. So, 2 and 5 are the eigenvalues, 2 and 5 are eigenvalues. So, let us go back and try to understand. So, I had A here, A was u d u star, fine. So, when I want to compute x star A x, I am looking at x star u d u star of x. So, I can write it as u star x whole star, d here for me is 2 and 7, 2005 and u star x, fine. I write like this. So, this is same as, I do not know what u is, but what we know is that every Hermitian matrix is diagonalizable. A is Hermitian, implies A is diagonalizable, implies there exists unitary u such that A is equal to u d u star. All right, this is what we are using, fine. So, I can take a u star x. So, if I look at u star will be some u11, or say let me write it as alpha, beta, gamma, delta, whatever it is. X is your x and y, fine. So, u star, so this is my u star I am writing here. So, u star x is equal to alpha x plus beta y, this is gamma x plus delta y, fine. So, I would like you to see that this is same as you are writing it star of this. So, alpha x plus beta y, this gamma x plus delta y bar 2005 times alpha x plus beta y, this is gamma x plus delta y. So, this is nothing but 2 times absolute value of alpha x plus beta y whole square plus 5 times gamma x plus delta y whole square, all right. So, you can see that this is positive for every choice of x and y and is 0 only when x and y is 0. Is that okay? I would like you to try that out yourself for the first example also, but the idea is that they come from eigenvalues. This is more important for me, that if you look at the calculation here, finally these eigenvalues are coming into play. Is that okay? If the eigenvalue was negative, I would have got a negative number here, fine. This is what is important. Second example. So, I have given you 2 examples. Now, let us look at, so this is about positive definite. So, both the examples were positive definite here, fine. Now, let us look at positive semi definite. So, I define A as, take A as 1 1 1 1, and so you can see here that 0 is an eigenvalue, 0 is eigenvalue with eigenvector 1 minus 1. So, check that 1 minus 1 times A times 1 minus 1 is 0, all right. So, I have a non-zero vector for which things are 0 here, all right. I can take over this root 2, 1 plus I, 1 minus I and root 2 here, another matrix A as this. If I look at this matrix, again look at the determinant of A. Determinant of A is 2 minus 1 plus I into 1 minus I, which is 2 minus 1 minus I square, which is 0, all right, fine. So, 0 is again an eigenvalue, 0 is again an eigenvalue, if x is an eigenvector of A corresponding to 0, implies A x is equal to 0 x, and this implies x star Ax is equal to x star 0x is 0. All right. So I do get 0 here. Is that okay? So this is what you have to be careful. You just have to look at eigenvalues. From there you can get eigenvector, and then you can get all those things. All right. Fine. Third example. So I gave you positive semi-definite. Now let me give you negative semi-definite. Negative semi-definite. I hope I've written it correctly. So my A is 1 here, minus 1, 1, and 1 minus 1. This is what I wrote here. Or you can take A to be equal to minus 2, 1 minus I, 1 plus I, minus 1. Check that this is negative semi-definite. So the one way to check is look at this part. At least I can try this out myself. The determinant of this is negative as well as the trace is negative, so it will be negative. Yes. So try that out yourself. Fine. Fourth one. Look at the trace is minus 2 and determinant is 1 minus 1, which is 0. Is that okay? So 0 gives you semi-definite here. Otherwise it would have been negative definite. Fine. So you can just take a larger number, make it negative and make it a negative definite yourself. Fine. A, which is 0, 1, 1 minus 1, or if I take A as 1, 1 plus I, 1 minus I, 1, all right, then this is A is indefinite. All right. So let's check this part. So x, y, 0, 1, 1 minus 1 times x, y. I want to compute this. This is nothing but this into this is y, this into this is x minus y. So x minus y times xy, which is xy plus xy minus y square, which is same as 2xy minus y square, which is 2 times 2x minus y into y. Fine. So there are choice of y, x and y, where you can see that this is positive, and if I take y to be negative or just take y to be very large as compared to x, even if it is positive, this becomes negative. All right. So this is an example of a negative definite matrix. Is that okay? So I would like you to construct these examples and understand the importance of eigenvalues and eigenvectors in this study. All right. So I would like you to see that all the calculations are going to be based on eigenvalues and eigenvectors here. Fine. Because I am looking at x star Ax. Since I am looking at x star Ax, we are also assuming A is Hermitian. Fine. So A is Hermitian implies that I can write A as U D U star, D is diagonal matrix of eigenvalues. Fine. So I can replace this by that I did earlier also, x star U D U star of x, which is nothing but U star x whole star D times U star x. All right. Fine. So you can see that that has come into play here. Fine. The way we did for the previous example, I think I did it somewhere. I did it here. All right. So you can see that this is the way I have played around here to get my things. All right. So this is the play that I have done. Fine. Same play is to be done here also in the general setup, that I have to find a diagonal and then everything becomes nice in some sense. And these are called what are called the linear forms and so on. Well, linear forms in the sense that you have this matrix U and then you are multiplying by x1, x2, xn. So this times this one will give you the first linear form, this row into this will give you another linear form. So there are n forms that you can get here and things like that depending on what your U is. Fine. So this is about the definitions and so on. Let us now concentrate slightly in what does it mean to say that A is a positive definite matrix or A is a positive semi-definite matrix and so on. Is that okay? So let's look at some theorems on this part. Theorem. So A belongs to Mn of C. So as stated, I am assuming that A is Hermitian, otherwise you will have to prove it yourself. then the following statements are equivalent. A is positive, semi definite. B, A star is equal to A. So, I am not stressing on this because I am already assuming, all right, and each eigenvalue of A is non-negative. C, A is equal to B star B for some matrix B, all right. So, this is what our assumption is, but so this part is our assumption. I do not want to waste my time proving it, you can try it out yourself, fine. So, proof. So, we are assuming that A is positive semi definite and we are taking that A star is A. We are already taking A star is A. Otherwise, I will have to prove that positive semi definite, or I will have to prove that X star A x is belongs to R implies A star is A. I will have to prove it. So, try that out yourself, all right. I do not want to waste my time, fine. So, as A is Hermitian implies A is equal to U d U star for some unitary matrix U and a diagonal matrix D with diagonal entries as eigenvalues of A. Is that okay? So, that is more important that they are eigenvalues of A, all right, fine. So, let us look at something very carefully. So, let alpha comma V be an eigenpair of A, fine. Then I want to look at V star A V. So, V star A V is equal to, just look at this part, V star A V is alpha V, fine. Since it is Hermitian, every eigenvalue is a real number. This is what we have seen already. So, this is same as alpha times V star V, which is nothing but norm of this, fine. This is a positive quantity. We are saying that A is positive semi definite. So, A positive semi definite implies alpha times norm of V square is greater than equal to 0, but norm of V square or norm of V itself is positive because V is an eigenvector. This implies alpha is greater than equal to 0, all right. So, we have proved that each eigenvalue of A is non-negative, fine. From there I want to go to C, that A is equal to B star B for some matrix B, fine. So, this I have shown that A implies B is done. Again have a look at it nicely. A is Hermitian implies A equal to U d U star for some unitary matrix U, and then D is the diagonal of eigenvalues, fine. And but anyway, I have not used that idea at all. I should have used it. So, this is to be used for the next part. I have to show that eigenvalue part. So, let alpha comma V be an eigenpair of A. Then V star A V is this expression, whatever I have written here. V star A V is this expression that you can compute yourself. We have been given that A is positive semi definite. It means that V star A V is greater than equal to 0. Positive definite implies V star A V is greater than equal to 0. So, therefore, this is greater than equal to 0, and therefore, alpha is greater than equal to 0, all right, fine. So, what we know is that all the eigenvalues are positive. So, D has all positive entries. So, I would like to write A as next part, B implies C. I have A as U D is lambda 1, lambda 2, lambda n 0 0 u star. So I write it as u square root of lambda 1, square root of lambda 2, square root of lambda n, this times this itself, root of lambda 1 till root of lambda n times u star. Is that okay? So I write like this. Define, I wanted to show B or B star, B, all right. So define B is equal to square root of lambda 1 till square root of lambda n 0 0 and u star. Define B as this. This implies B star is equal to u star star, which is u, and a star of this. This is the diagonal matrix, so it will remain same. I have to take complex conjugate, but lambda is a real non-negative. All right, so each lambda is non-negative, so square root is a non-negative number, and therefore there is no complex number coming into play. So it will be just lambda 1 till the square root of lambda n itself. Is that okay? So this is what we have, because as lambda I is greater than equal to 0 implies the square root of lambda I is also greater than equal to 0. Is that okay? So therefore we are getting this part. So you can see from here that A is equal to B star P. Fine, we have done that part. Now C implies A. So given A is equal to B star B, to show A is positive semi-definite, or which is same thing as showing that x star A x is greater than equal to 0 for all x belonging to C, and this is what you have to show. So let's compute that part. So by definition, or by what you by given assumption, by assumption, x star A x is equal to x star B star B x, which is same as x star B star into B x, which is B x whole star B x, which is nothing but norm of B x whole square, and which you know that the length of anything is greater than equal to 0. So this is greater than equal to 0 for all x belonging to C n. All right. So we have shown that all the three are equivalent to us. Is that okay? Nothing special. We have done that part, very simple. Now I want to write it in terms of positive definite matrix. So theorem, again A belongs to Mn of C. Fine. The following statements are equivalent. A is positive definite, so semi-definite has gone, it is only the definite that you are looking at. B, A star is equal to A, and each eigenvalue of A is positive. So from non-negative we have gone to positive. And C, A is equal to B star B for some invertible matrix B. Fine. So again let's go back and understand that positive definition implies that x star A x is positive for x not equal to 0. All right, fine. So when I look at eigenvector, so if alpha comma v is an eigenpair, then what we know is that alpha times norm of v square, as you computed earlier, this is same as alpha times v star v, which is same as v star alpha v, which is same as v star a v. All right, fine. This says it is positive, it means that this is positive, so this implies alpha is positive. Fine. So just writing things the same thing again and again and nothing else. So 1 implies 2 I have done, A implies B. Now let's look at B implies C here. Fine. We want to show that every eigenvalue is positive implies that A equal to B star B, but we want that B to be invertible here. Fine. So let's look at B here for us. B was this matrix, fine. So when we are saying that the lambda i's are positive, what does it mean? Lambda is positive means a square root of lambda 1, a square root of lambda 2 till a square root of lambda n, each of them is positive, and therefore this matrix B is positive, alright. So if here itself, if the square root of lambda is positive implies B is invertible, alright. So we get that B is invertible and we have been able to write A equal to B star B, fine. Similarly here also, since you are going to assume that this is positive, so now we are going to assume that this is positive, fine. So we need to show, alright, A is positive definite, so need to show V star or X star AX is positive for all x belonging to Cn. So just compute X star AX, which we computed earlier as Bx whole square. I have to show this is this, fine. So to show that this is positive for all x not equal to 0, this is what I have to show, fine. So look at this equal to 0, alright. Now norm of a vector is 0 only when the vector itself is 0. So since I am saying that the norm square is 0, so norm is 0, so implies that Bx is 0, but we have been given B is invertible. Well, what does invertibility mean? Invertibility means that this system B is invertible implies the system Bx is equal to 0 has only the trivial solution x is equal to 0, alright. So what we have seen here is that, fine, that this can be 0 or this can be 0, X star Ax can be 0 only when x is 0, alright. So we have shown that all these three conditions are equivalent. A is positive definite implies A star is equal to A. I have not proved that part, you have to do it yourself. I have shown that the eigenvalues are positive. Eigenvalues are positive means this happens and invertibility comes because of each lambda I is positive, fine. And from here we go to this because B is invertible implies the system Bx is equal to 0 has only the trivial solution, alright. So I end this class here itself. We will look at the next ideas in the next class. Thank you.